Hey everybody for joining my talk today. I will be talking about the Allen Telescope Array in general, what it is and how we can use it, and how we can use it for FRBs in particular. I'd like to also thank the organizers for this meeting. The meeting was great, the food was excellent, and yeah, let's get started. Okay, so what is and where is the Allen Telescope Array? So the ATA is located in Hat Creek, in the Hat Creek Radio Observatory. It's in California. If you drive, if you land in San Francisco and drive 5 hours north and a bit east, you get to the Hat Creek Observatory. This is the view from Google Earth, so you can actually see the small dishes up there. The ATA is one of many instruments up there. You might have heard from our chime collaborators that there's a chime outrigger up there on site as well. But I'll be focusing on the ATA and the ATA effort. But please feel free to ask me about other stuff happening on site. The ATA in particular is a 42-element, 6-meter dish in design, interferometer in design. It operates in the 1 to 12 gigahertz band. So its RF system is sensitive to 1 to 12 gigahertz, which makes it pretty unique in this, in FRB land at least. And it has an extremely flexible analog and digital system. So as just a quick overview of how the telescope works. So the feeds are log periodic in design. They are pretty much bunch of Yagis, similar to the ones that Vers was showing earlier. But basically 2 Yagis that are put in a cryostat and cooled down to roughly 60 Kelvin, just to reduce the noise, to make the instrument a bit more sensitive. There's an analog signal, or the signal gets sent through analog down to a central processing room, where there's some black magic happens down there. The signal gets split into 4 and get digitized 700 megahertz at a time. So in other words, we have 700 megahertz times 4 anywhere in the 1 to 12 gigahertz band. There's a bit more technology happening on site. We're testing a new system, a new feed called the quadridge feed. Something like this can go from 1 to 20 gigahertz, so it's already an upgrade to what we have. And we have that prototype for the first time on one of the ATA feeds or ATA dishes, and we're currently testing that as we speak right now. So this is really exciting stuff happening. Also looking forward a bit. Rather than sending the analog signal down and doing this black magic tuning thing, we can actually try to digitize directly on the telescope, and this would allow us to do the 1 to 12 gigahertz instantaneously. Now this is not going to happen anytime soon. This technology we're still testing. We're actually waiting for this evaluation board, but this is something you can ask me about if you're more interested. In terms of observing modes, what we can do with the ATA, it has the basic vanilla sort of radio telescope, radio interferometer observing modes. We can use something called the voltage record system, where we dump all the voltages to disk. This is something that we don't use on a daily basis. You can get swamped pretty easily with the data rate. There's a continuum correlator, basically a software correlator, basically a software cross-correlation process where we take every pair of antennas and we cross-correlate them together. The reason why we do this is if you want to form images of the sky, radio images of the sky, you have to use the correlator, but also you can calibrate the beamformer. The beamformer is simply a summation of all the antennas. So you can either multiply all the antennas together or sum all the antennas together with the beamformer, and this is what we use to do FRBs. If you sum all the antennas to a particular point source, which is an FRB source, for example, in this case. We're also testing a spectral line correlator, which I'll show some images of in a second. Some testing that we've done with the correlator, you've probably all seen the nice Milky Way galaxy sort of image by Meerkat. If you try to replicate something like this with 4 hours of the ATA, we end up with something on the left, which is actually pretty cool. I was pleasantly surprised when I saw this image, and you can see sort of the filaments there. This is a hydrogen or L-band continuum observation. Another thing we can try doing is using the hydrogen line, the neutral hydrogen line, and trying to observe, in this case, Andromeda. So this is also something I've done in the process of commissioning the spectral line correlator. And you can see that we managed to get the integrated flux with the nicely sort of rotational velocity field of the of Andromeda. In terms of the science program, I'll focus mainly on FRBs here, but we have sort of interesting other sort of science that we're doing, including search for extraterrestrial intelligence, so looking for narrowband signals that are proxy for intelligent life. We're also doing slow transients, including follow-up of GRBs, also studies of tidal disruption events and extra-binaries and others. Bits of pulsars and blazars, but FRBs is mainly the focus of my talk, at least now. I also mentioned that the ATA is a nice place to do sort of training and education, so this is something we're also focusing on, and also to prototype new technologies, as I mentioned earlier. We're also looking into something called the National Radiodynamic Zone, which is kind of the a slightly different way to protect radio astronomy by rather than doing a national radio quiet zone, like what the Green Bank Telescope or the Green Bank Observatory has. Quiet zones cannot be enforced anymore, given that we live in a society now where communication services are heavily implemented. And so the National Radio Dynamic Zone is a way to communicate the use of the electromagnetic spectrum with transmitters and receivers. And so that's something we're also working on in Hat Creek. Okay, so let's talk FRBs. Owning a telescope and operating a telescope gives you sort of access to a few hundreds of hours to do whatever you want with it. And so one of the very few things that we've done is to follow up on hyperactive repeaters. And FRB 2022-0912A was one of them. That was sort of the second, I think, FRB that we detected. I think FRB 2020, forgot the phone number that we detected, the first detection with the ATA. But this is an FRB that we focused on back when we knew it was hyperactive in 2022. So we had 541 hours of observing. We detected 35 bursts. Actually, that number got bumped up to 100. We had some changes in our back end, and we actually missed a good fraction of our bursts. So now we have actually around 100. So we're preparing a new publication about this that we'll hopefully have in the next few months. But basically, this is the zoo of the bursts that we've detected. Most of them are downward drifting, sort of the classical repeating bursts. The nice thing about this is that we have continuous monitoring, and because the ATA it's not as sensitive as other telescopes, but we have good observing time. We can actually try and monitor the tail end of the distribution, the bright end of the distribution in energy of FRBs. And we can do things like this. Basically, I'll have to also advertise this is a paper that we written last year. Sophia Sheikh, my colleague, led this work. But basically now, because you have 35 bursts with subpulses, you can try to extract some of the features from this data. And as I think Ben mentioned earlier, is trying to figure out if there's any relationship in the burst parameters that might help theorists to uncover the emission mechanism of FRBs. And so if you plot something like the bandwidth as a function of the center frequency, so you take every single FRB, figure out where exactly it lies in the band, and what's the spectral extent, and plot it, you end up with something like this. I know that other works have also done, I think in FAST as well, they've done something similar. So it's good to put results out there. You can also plot the distribution of the burst energy and then width and duration and so on and so forth. One thing we also mentioned in that paper is that again, so the ATA is sensitive. It's not very sensitive compared to other high sensitive telescopes, but we have enough time to actually sample the high end distribution of the FRB. And so what we did is basically manage to say that there's a cutoff frequency, cutoff lumens of that FRB, which corresponds to a cutoff energy of 10 to the power 32 to 10 to the power 33 ergs per hertz. And this also would help in sort of putting limits on emission mechanisms for FRBs in general. And something interesting also is that the repetition rate above 100 Jansky millisecond is actually a few percent of the all-sky rate. compared to the results that are got by other instruments. So this also puts limits on the cutoff energy of FRBs. Okay. Another FRB that we've been also closely monitoring is FRB 2024-0114A. This FRB we have a bit double of the observing time. Again, using the ATA, we have a high spectral coverage that we can utilize. Currently, we're utilizing 2 times the 700 megahertz or 2 times the tunings. This week, I think we'll have up to 4 tunings, so that will allow us to do more instantaneous wideband studies. But for this FRB, we have 97 bursts in roughly 1,200 hours. I think I have a typo in there, but that's fine. There's a bit of spectral and temporal, structure in these bursts. This is the observing time, basically as a function of frequency. The few things that we see, and something that we've mentioned in earlier discussion, is that this FRB kind of shows temporal and spectral sort of variation for some of the bursts, but some of the bursts just look kind of boring, plain single blip. The nice thing about this is that it went all the way up to 4.8 gigahertz. So we have that wideband detection with it. Something this is work in progress, is to figure out what is the spectral distribution of these bursts. And so the first thing we've done is to count the number of FRBs at a given frequency. And we see something like this, which just means that the burst rate at S-band, so between 2,000 and 4,000 gigahertz, is slightly higher than L-band. But there's a bit more work to be done here, so this is really preliminary at this point, because obviously RFI, or radio frequency interference, is more prominent at lower in L-band, and more work needs to be done. And I'm almost there. So that's my summary. The ATA is kind of leaving now the science commissioning phase. We have new technologies being tested, and in terms of FRBs, we have wideband monitoring of hyperactive repeaters. So let me know if you have any questions or are willing to collaborate. Thank you.
Yeah, 2 minutes for questions.
I might have missed it, but what's the localization precision of the ATA?
Yeah, so that obviously depends on the baseline and what observing frequency you're using. So in L-band, the localization, the ellipse is basically the localization region is basically an ellipse. The short axis, or the small axis on that localization, is around 2 arc minutes in L-band. Going up to X-band, it decreases by a factor of 8. So you get up to maybe half an arc minute.
Other questions?